Welcome to the presentation and good morning. Yeah, today I'll present our work, that is Rudraksh. It is a lightweight and compact key encapsulation mechanism which we have designed, and this work is a joint work with Purdue University and IIT Kanpur. Without further ado, we'll start. And this is the outline of this talk. I'll start with the background and motivation of lightweight PQC, and then I'll go for designing lightweight key encapsulation mechanism, and finally I'll show our results and compare with state of the art, and finally I'll conclude the talk. Now I'll start with current status of post-quantum standardization procedure, which was like going on for almost 8 years almost, and NIST was one of the leading candidates among them. They have selected Kyber and its QC as a key encapsulation mechanism, and dilithium spins plus and Falcon as a digital signature. Later, welcome. Yeah, and I just started. It's the second slide. Yeah, and there are several other countries which has, most of the countries actually, who actually followed NIST standard recommendations, along with some extra candidates such as classic Macaulay's and Frodo-KEM. However, there are some countries such as South Korea who has taken a very different approach. They have organized their own PQC standardization or competition, and they have selected this N2 plus and SMART-T as key encapsulation mechanism and AMER and HT as digital signature. Those are pretty different than the NIST standard. And very recently, China has announced that they will also start a post-quantum standardization procedure. So this is kind of the standard situation right now for post-quantum cryptography. And in this work, we'll go beyond standard. Like after the standards, we still need some extra care for other specific applications for PQC, and we'll go there. Now, why we go there? This is kind of the motivation for this work. And there are several applications which requires post-quantum standardization, post-quantum cryptography. And most of the post-quantum standardization candidates, those who are designed for general purpose use cases. And however, there are several other designs as well. And this is a picture of the applications which needs cryptography, which includes resource constraint devices, and that connects to, let's say that's connect to the gateway. It's the right-hand side picture. And it requires, like, it prefers low area or power compared to like latency or compared to like the speed of the communication. Now there are devices which are powerful, and that serves like thousands or millions of devices at a single time, at a point. And for them, low latency or high throughput is more important than the low area or memory. Now there is also some devices which are resource-rich devices, such as our laptop or our systems that we use, that has kind of moderate or high latency or throughput tolerance, and also it has like medium or high area or like medium area at least, and also energy. Now, although NIST standard has been done, there are situations when NIST adapt more improvements, the improvements which goes on in the community. And one such example is the addition of new elliptic curves in the standards or in the special publications of the standards. And this is kind of an example where it shows like NIST adapts with new improvements. So it's not like the post-quantum standardization by NIST has been done, so it's finished. So we still work on it. And another thing is lightweight cryptography. As I mentioned in the beginning, we will focus on resource constraint devices, and that is kind of a purpose of lightweight cryptography as well, that tries to provide security in lightweight or resource-constrained devices. It's not weak security, but it's lightweight. So one such example is like there was block ciphers for AES and also Keccak response cipher, Keccak-based one for SHA-3. However, NIST still organized the lightweight cryptographic standardization procedure to select sponge-based ASCON for resource-constrained devices. So we definitely need lightweight cryptography as well for several applications. And this is kind of one example of that situation. So now finally, goal of this work. So that is, in this work, we aim to design a key encapsulation mechanism that is dedicated for tiny hardware devices such as IoT. And also, we didn't want to compromise in security, the chosen ciphertext attack security. That is also very much needed for several applications. And here we have tried to design from hardware feedback. So it's kind of a like hardware-driven design decision we have taken in this work so that we can achieve the lightweight implementation together with and we have taken that during design time. All the design decision has been taken from the feedback we get from hardware designers. So first thing, when we start designing a key encapsulation mechanism, we first need the hard problem, which is computationally hard problem that gives security for public key cryptography. So we started with the hard problem. First we selected the hard problem and then we go forward with the work. For the hard problem, as we plan to use learning with error or one of those variant, so we started looking into learning with error problem first, which is, the instant of learning with errors. It has, this is the matrix and vector of the learning with error instance. So, and it has very huge matrix vector multiplication, which is pretty expensive, has larger keys, and also the best thing is it provides strong security, or it's the oldest problem we have for LWE-based LWE problem. And one example that used this, one example of key encapsulation mechanism that used this problem is Frodo. And now an optimized version of this problem for to achieve a smaller key. It's ring learning with based instances. Here we replace all the matrix and vectors by polynomial, and that actually helps us to achieve faster speed, faster performance, and also there is some debate about its security because of its structure. However, there are several schemes which uses this hard problem, and one such example is New Hope. Now, in between these two instances, there is another instances that's called learning with module LWE, and that is a trade-off between LWE and ring LWE. So it provides strong security reduction. However, it also has matrix vector multiplication, but it has polynomial inside it. So it's polynomial a little bit smaller than ring LWE. However, and also its matrices are also smaller than standard LWE. And with when we have similar dimension, which is n for that matrix dimension for n LWE, and which is also the polynomial size for ring, which is equal with the matrix dimension of the module dimension and also the smaller polynomial. Its multiplication is if those are equal, this equality is satisfied, then these three schemes provide similar security. So security-wise is fine. And one example which uses this instances or this hard problem, that is Kyber, which is the current standard. Now, in this work, we started with modulus space exploration. This is a diagram where we have learning with rounding and learning with errors problem, and all the schemes which are in color green, those already exist. And in the right-hand side, there is standard hard problem-based schemes. And on the left-hand side, there are ring LWE-based schemes, ring LWE or LWR-based schemes. And in the middle, in the gray box, there are module learning with errors or learning with rounding-based schemes, which I have taken from the literature, which I have observed. And after gathering all this key encapsulation mechanism, what we observed that module space hasn't been explored that much, at least for learning with error-based key encapsulation mechanisms. So we decided to explore this area. We have designed three new schemes, decided to design three new schemes, one with the polynomial size 32, another with polynomial size 64, and another with polynomial size 128. These are these three. And if you notice, if we go towards from standard to ring dimension, then the performance increases. However, if we go towards like standard to ring direction, then the memory consumption also increases. So, and we wanted to have list memory as well. So we wanted to have a trade-off in between. Now, another important thing for post-quantum key encapsulation mechanism, that is it uses random number generation and also hash function. That those are auxiliary function. However, those are Keccak based, so they takes almost 50% of area and memory. And that is also one of the bottlenecks of these schemes. So we plan to replace it with the lightweight standard ASCON. And what we observed from the literature that ASCON requires list area and also has frequency-wise it's also higher, and throughput per area is also lower compared to Keccak. So that's why we have decided to take ASCON instead of Keccak for our lightweight design, for our lightweight key encapsulation mechanism. Now, another decision we have taken to design this lightweight key encapsulation mechanism, that is careful hardware scheduling. And that is to reduce the memory requirement as much as possible. We have used two hardware components. One is ASCON, another is the butterfly unit that is needed for number theoretic transformation to do polynomial multiplication. And if you notice that, yeah, it takes almost similar amount of time, those two blocks, so that we need least amount of area, and that's also take least amount of time. And after all this step, we went for finding the parameters, and like there are three actually primary parameters to design, which actually makes a scheme different than another scheme. That is, those three are that underlying lattice dimension, which is like in the polynomial dimension into matrix dimension for the modules, and that is here n prime, and also the modulus, that is Q here, and the noise distribution, standard deviation of the noise, that is eta. So if you notice, this is the failure probability and security graph. I think you can see my cursor, yeah. And here, like this, both of them are kind of security parameters. So we need to have a balance between them. And when we increase that underlying n prime, underlying lattice dimension n prime, and by keeping Q and eta fixed, then our failure probability and security both increases. Whereas if we vary Q by keeping other two fixed, then both failure probability and security decreases. And when we vary eta by keeping other two fixed, then also failure probability and security increases. So it is kind of, we have to make a trade-off to find the final parameters for each of the scheme. And we have designed these first three schemes, which are KEM poly 32, KEM poly 64, and KEM poly 128. This is the parameters. I'll not bore you with this description. However, when we estimated the memory cost of these three schemes, together with Kyber and Niho, we observed that the scheme with polynomial 64 that takes least amount of memory. Therefore, we have decided to choose this scheme and implement and call it Rudraksh and implemented it in a lightweight manner, the method I showed in the beginning. And by doing that, and also another last thing that is, I wanted to mention that we also explored the number theoretic, like the butterfly modulus for, like especially the modular reduction to make the butterfly for the number theoretic transformation. As here we are using, for Rudraksh, we are using 64-point entity, and we have also tried to use several modular reduction for it. And we observed that shift and add kind of modular reduction took least amount of area. So we have chosen that one for our modular reduction. And also another thing, please note that for k-square reduction or those two reduction, this needs extra polynomial multiplication, so that's also cost speed. And after all these design decisions, we finally implemented it and implemented it on Vertex 7 and Arctic 7 platform. And we observed that Rudraksh provides 3x area improvement with respect to state-of-the-art area optimized implementation of Kyber. And Rudraksh can operate on approximately 60 to 75% higher frequency with respect to Kyber, high throughput Kyber. And Rudraksh improves the time area product approximately 2 times with respect to compact implementation of Kyber. And the key takeaway of this talk is there are several applications. For them, we need low power or low area, and that is more important for them compared to the latency or throughput. And this was the first attempt to make a CCO secure lightweight post-quantum cryptographic key-encapsulation mechanism. And it was also kind of, as far as we know, first scheme that is hardware driven, or we have taken hardware cost into our consideration while designing the scheme. And also, as we have used modular lattices here, it's also provide flexibility. Here we have focused on area optimization, so we have tried to make it as least costly for area as possible. However, it can also provide speed if we parallelize it and if we have enough area. And also here we have applied ASCON as our PQC, as a symmetric primitive in PQC. And we have also finally we have implemented Rudraksh on hardware as optimally as possible, and we have achieved we required 1/3 area compared to Kyber state-of-the-art area optimized implementation. And if our paper can be found in the ePrint in this link. Thank you for your attention.